Hi, this video is about the Poisson and hypergeometric distributions. So the Poisson is kind of unique. It involves rates. So random occurrences sometimes happen at a steady long-term rate. So say, for example, customers enter a shop at a rate of 5 every hour. Now, it's not going to happen that every 12 minutes somebody enters. It's still going to be random, but in the long-term average, the rate is pretty stable like that. So then if you have a fixed time interval, you can use the Poisson formula to find the probability of any total number of occurrences. And the formula looks like this. Okay, there's a couple strange things. There's the exclamation point. That's called factorial. Anyway, that's in your calculator. You can find it there. It's probably somewhere near NCR. It has E, which is again about 2.72. That's also in your calculator. And it has this Greek letter mu, and mu is the expected number of occurrences. Now, this depends not only on the rate, but it also depends on the length of the time interval that we're looking at. So let's see how this works. Say we have a shop where customers enter at a rate of 2 per 5 minutes. That's my rate. Find the probability of 6 in 12 minutes. So I got to start with 12 minutes. At a rate of 2 per 5, in 12 minutes, I'd expect a total of 4.8 people. Now, the chance of getting 6 people, just plug that in, and you get a probability of about 14%. Now, if I have the same shop, the same rate, but this time I'm focusing on just 1 minute. At that rate, in 1 minute, I'd expect 0.4 people. Now, the chance of getting at least one person is 1 minus the probability of 0 people, and I get an answer of about 33%. Okay, next example. So we got a factory. And the rate doesn't actually involve time at all. It's 1.5 defects per 1,000 units produced. But that's still a rate, so it doesn't really matter. I'm going to have a fixed number of units produced, though, to find my expected value. So I want the probability that the first defect is sometime after the 600th unit is made. Well, that implies that there must be 0 defects in the first 600 units. So 600 units is my fixed time interval. It's not time, but whatever. At a rate of 1.5 defects per 1,000, in 600 units, I'd expect to get 0.9 defects. So the probability of getting 0 defects, just plug it in. It's about 41% almost. Okay, now an interesting consequence of the Poisson is that non-overlapping time intervals are independent. So I've got an airport and planes land at a certain rate. So I'm going to look at 2 non-overlapping time periods, 40 minutes followed by the next 90 minutes. So in 40 minutes, I'm looking for 1 plane, and the following 90 minutes, I'm looking for 3 planes. And because they're going to be independent, I can just take the 2 answers and multiply them at the end. So let's focus on the first 40 minutes. Now, in 40 minutes, at the rate given, you'd expect 1.4 planes to land. So the probability of getting 1 plane is 0.3452. Then in 90 minutes, at the rate given, you'd expect to get 3.15 planes. So the chance of getting 3 planes exactly is 0.2232. And because they're independent, I can just multiply those 2 together to get my final answer of 0.077. Okay, let's try another example. So this is also an example where the rate is not about time, but it's per page. A writer makes a certain number of mistakes per page. But that's fine. We have a total of 12 pages, so we know what's going on. Now, if you look carefully at what's happening in this question, we have an overall structure that's actually binomial. There's 12 pages total. That's like n. And I want to get 3 successes and 9 failures. 3 pages that have at least one mistake and 9 pages with no mistakes. So actually we have an overall structure that's binomial. N is 12, but I have to use the Poisson formula to figure out P. Okay, so the chance of getting at least one mistake is 1 minus the chance of getting no mistakes. By the Poisson formula, that is 0.259. Now, that is going to serve as the P in the binomial formula. So to get 3 pages with a mistake, you run through the binomial formula, you get an answer of 0.2574. So certain questions are like this. They have an overall structure that's one distribution. In this case, the overall structure is binomial. But you have to use other distributions to figure out the pieces. Okay, moving on to the expected value and variance. Well, in Poisson, it's remarkably simple. They're both the same number. They're both the expected value. Okay, so let's see how this works. Let's say we have an intersection that cars go through at a rate of 25 per minute. All right, let's find the expected number of cars in 1 hour and its standard deviation. So 1 hour is 60 minutes. So the expected number of cars is 1,500. And that's the expected value. Well, that's also the variance. So you square root that and you get the standard deviation. So the hypergeometric distribution is all about the questions we've seen before about we have a jar and it has two colors of ball in it. So there's a lot of symbols that we need to use. We have capital N is the total number of objects, and there's 2 kinds of objects, good and not good, and we're going to pick little n of the objects without replacement. So capital G is the number of good objects, therefore capital N minus capital G are not good. And out of n objects that we pick, we can get a certain number of good objects, and this formula gives us the probability of getting that many good objects out of n total picks. So this has nothing to do at all with the geometric distribution. The name's a little bit confusing, I guess, in that respect. It's all about NCR. We keep using that formula over and over in this one. Okay, let's actually use it. Say we have a shipment of 25 microchips and 20 are broken. So that means 230 are good. So that's going to be my capital G. 250 is capital N. And I'm going to pick 5 of them, so that's little n. And I want the chance that they are all fine. So the probability I get 5 good objects, if you plug the numbers in and do all the NCRs, you get an answer of about 65%. Okay, same basic setup. I have 250 objects, 230 of them are good, but now I'm going to grab 15 of them, so little n is 15. I want the probability that at least 2 of them are broken. Well, I'm going to do 1 minus the chance that 0 are broken or 1 is broken, which, if we switch to thinking about good objects, that's 1 minus the probability of getting 14 good objects or 15 good objects. And plugging those numbers in, we get an answer of 0.3416. So the expected value and variance of the hypergeometric distribution goes by these two formulas. If you think of capital G over capital N as similar to P in the binomial distribution, then you'll see some strong similarities. It looks a lot like NP and NPQ for the variance. So there are some striking similarities there. But let's actually use these formulas. Card games follow the hypergeometric distribution because when you get the cards from a deck, it's obviously without replacement. Okay, so you get 5 cards, and I want the expected number of spades and its variance and standard deviation. So there's a total of 52 cards. 13 of them are spades, and we're going to pick 5 cards. So by the formula, we expect 1.25 spades with a variance of 0.864. Square root of that is 0.9295, and that's your standard deviation. All right, so we learned 4 distributions this week. And again, by far the most important was the binomial, but no less interesting was the Poisson and geometric and hypergeometric. So it's a lot to take in, and I'll see you